Welcome to the third lecture in quantum field theory. Today we will derive the Dirac equation. So in the past few lectures we took a look at the Klein-Gordon equation and we tried to see if it could be a viable option for a relativistic quantum mechanical theory, but we saw that there were just too many problems, right? With the probability density that could be negative, we just saw that it didn't really make any sense, and the problem arose mainly from the fact that it was a second order equation in time, and that's where the negative probability density came from. So even though it did successfully treat space and time in the same way, right, both in second order derivative, it just was not good enough. So now what we will do is try something else. So what comes next would be, well, second order didn't work, so let's try to build something that is just first order in time, right? So one time derivative, one space derivative. So, well, how do we do it? Well, we can now look to the main equation that we have been using to describe relativity when we put it combined with quantum mechanics, which is of course E squared equals P squared plus M squared. P, of course, being the vector for momentum. So this is what we want to work with. But here we can see that any relationship, right, that is not squared for the energy will be something like P squared plus M squared inside of a square root, right? If we solve for the energy and we want to build some sort of Hamiltonian that contains this, I mean, yeah, we already have a square root and that's not going to be linear, which is what we want. So how do we possibly build an equation that is linear in the time derivatives? Well, Dirac had a very smart idea. He said, well, although this expression may not be linear, right? Perhaps we can't really find a linear expression in terms of these scalars, but perhaps we can do it not by taking the square root like we have been doing, but by taking a matrix square root. So what is a matrix square root? Well, a matrix square root is simply, right, if we have some matrix A, and this matrix A can be written as B times B, where B is another matrix, then B is called the matrix square root of A, right? So this would be the matrix square root of A if this is true. So what we want to do now is try to basically go from this just simple linear expression into a matrix formulation. And how do we do it? Well, let's see that we can rewrite this as E squared minus P squared, which is equal, of course, to M squared. And we know that for vector P, or rather P mu, this is E, comma, the vector P, right? This is something we have seen in the past. I'm going to get rid of that dot so that it doesn't confuse you. So what we have here is simply P mu, right? It is simply the dot product in 4 dimensions of P mu with itself, right? Which is of course simply P squared, but now this is P vector, this is the 4 vector P squared, and this is equal to M squared. So what we now want to do is basically find the square root of this expression. All right, that's what we want to do. We want to find some matrix that is going to be the square root of the expression that we have here. And this is where Dirac had a pretty amazing idea. So what Dirac did is that he said, okay, let's define the matrix square root of P, or rather of P squared, as P, right? P and this line, so which gives us P slash. And he said, okay, this will be some matrix gamma mu that is to be determined. And why gamma mu? Because there are 4 possible gammas. And why do there have to be 4? Because we're going to be multiplying this with our 4 possible values for P mu. Okay, so that's why. And this is what he defined as this square root, the matrix square root. And this notation is very important. Overall, whenever we, from now on, write A slash, we mean that we are going to have this gamma matrix, gamma mu, multiplying the, well, whatever quantity it is that is in front. Okay, so that's going to be a very important notation from now on. I guess, well, maybe I shouldn't delete it. So this is what Dirac defined. Now, what do we know about the gamma matrices? Well, overall, what Dirac said is, okay, we don't really know much about it, so let's just be very, very, very general, okay? So let's say that these for gamma, these y4, again, because of this mu, right? We need 4 in order to do this product. So let's say that these 4 matrices gamma mu are just square n by n matrices, okay? We don't know what n is, right? N is just the dimension. We don't know if it's going to be 2 by 2, 3 by 3, 1 by 1, 5 by 5. We do not know. So let's just look at our definition and see what the very definition requires, right? Because what we want is for p slash to be equal to p squared times the unity matrix, right? And the unity matrix in n by n. Now this is my beautiful notation for the unity matrix. You may use I, n by n, it doesn't matter. Okay, so this is the unity matrix, unity in n by n dimensions. Okay, so just 1, 1, 1, blah, 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 all the way to 1, n by n, and 0, 0. Okay, so this has to be true by definition, right? We defined this gamma mu so that it fulfills this requirement, and now we need to find properties for the gamma matrix so that we can eventually figure out what it can be. Okay, so just looking at this, now let's write the definition for these things, right? So we know that p slash is going to be gamma mu, p mu, and then we have another p slash, but now be very careful. And this is why this is also a very good exercise to start being a bit more comfortable with 4 vectors. Because now, and just the tensor notation overall, gamma mu, we already used mu. So for the second part, we shouldn't use the same letter. So we should go for another Greek letter, because these things are kind of combined, right? These are going to be multiplying. This has this implicit sum, right? So we can't just put something with the exact same variable right alongside it. So for that reason, let's just say gamma nu and p nu for the second ones. Okay, so that these ones correspond to that. Okay, and this of course has to be equal to p squared times the identity matrix n by n. Okay, now what can we do? This is another good exercise to understand how we can manipulate these matrices, although I will have an entire video dedicated just to dealing with gamma matrices in time, because they will be very important. Okay, but what is this operator, right? This operator is basically going to be I h bar, even though h bar is 1 in our notation, d mu. So this is a spatial derivative, but our gamma matrices, they will not depend on time. They will be some constant matrix. They will not depend on time. They will not depend on space. So they will not be affected by the derivative in the momentum operator. So for that reason, we can simply commute this, right? We can just write this as gamma mu, gamma nu, p mu, and p nu. And this is, of course, equal to the same thing as before. So there we go. Okay, so we found this expression. Now we're going to do the same thing again, but slightly different. Because we want this to be true regardless of the order of our indices. And we also want to build a commutator or anti-commutator, because algebras are usually defined in terms of anti-commutators. Now, what exactly is an algebra? We will have so much time to talk about it. I'm again just spoiling some of these terms, and we will dive in more deeply. So what we now want to do is do the same procedure, right? So we start off with the exact same equation, and this time we will just call them differently. So we will write first gamma nu, p nu, and then gamma mu, p mu. All right, so, and other than that, it's going to be the same. We are going to just commute these two terms here. So we get gamma nu, p, sorry, I just said we commute them. So we get gamma mu, p nu, p mu. And this is a p squared, the unitary matrix, n by n. Okay, now we can add these two expressions together, right? So we add them together. So we get gamma nu, gamma mu, p nu, p mu, plus gamma mu, gamma nu, p mu, p nu, and this is equal to 2 times p squared times the identity matrix. Okay, so now notice that these two things are going to be equivalent. Why? Because these things, again, contain just some derivatives, right? These are just some space and time derivatives, and you can commute that, right? It doesn't matter if you derive first with respect to x and then with respect to time, or the other way around. That doesn't make any difference. So you can just change the order of those. Okay, you always have to be careful whether or not things commute when we are in QFT. Okay, sometimes they will, sometimes they will not, as we will very soon see. Okay, so now that we have the same thing here and here, we can factor it out so that we get that gamma nu, gamma mu, plus gamma mu, gamma nu, times p mu, p nu. This has to be 2 times p squared times the unity matrix. So if we want this product, let's divide by 2. So what we wanted, right, was that this product basically gives us this thing right there. So for this entire equation to be true, right, how can we have it so that these 4 vectors give us p squared? Well, what we need is eta mu nu times p mu p nu, right? Because when we multiply by the metric here, what we will get is p nu, and this is p squared. Okay? So this is what we need. This is the expression that we want. So what we can do here is just basically multiply by the inverse if we want, right? So the inverse of the metric is itself, as we saw in the very first lecture. And if not, I will just recall it because I'm not entirely sure if I mentioned it. But the metric in our notation is 1 minus 1 minus 1 minus 1, although there are some notations where it's the other way around, so minus here and everything else positive. But it doesn't matter, right? It is independent of notation. So what is the inverse of this? Well, the inverse we can clearly see here. If we want, right, the inverse by definition, if we multiply it by this matrix, it gives us the unity matrix. So if we multiply this matrix by itself, this element will be 1, this will be minus 1 squared, which is 1, this is minus 1 squared, which is 1, this is minus 1 squared, which is 1. Okay, so the inverse of the metric is itself. Okay, and why is that relevant? Again, because since we want to, we don't have eta mu nu here, we only have p mu p nu. So what we, whoops, I went one too far. So what we do is we say, okay, p mu p nu, this is simply eta mu nu p nu p nu. And that is something that we can now plug into our previous equation. So we have 1/2 gamma nu gamma mu plus gamma mu gamma nu. And now we have the metric tensor here. We have now it's p nu up here, p nu down there. And this is equal to p squared times the unity matrix. And there we go. So for this to be true, we need this right here to be equal to the unity matrix, right? So we need 1/2 gamma nu gamma mu plus gamma mu gamma nu times the metric to be equal to the unity matrix, right? Because this and this is already equivalent. And here, of course, we can again multiply just by the inverse of the metric so that we can put it on the other side. So this is simply eta mu nu times the unity matrix. And this is how we defined the algebra that we have. I will get into detail very soon. And this, by the way, actually, let's define it like this. So let's multiply by 2. So this will be 2 times the unity matrix times the metric. And this is what we define as the anti-commutator of gamma nu and gamma mu. And we write it as these brackets with a plus. Sometimes you will see this notation as this, so with these curly brackets, but that's the same notation that many people use for Poisson brackets, which is why I'm going to stick to to just brackets. But keep in mind that both of them are perfectly valid. So this is what we call the algebra. This is what defines the way that our matrices will work, and this basically gives us everything, right? So this is what gives us the properties of these matrices for everything that we want to do. And it is kind of weird, right? It is kind of crazy to think that this simple equation, right, gamma nu, gamma mu, as an anti-commutator is 2 times eta mu nu times the unity matrix of n by n. This defines all the properties, and it is weird, but I will show you how this does it and how that allows us to find many useful things. All right, so this is, by the way, something called the Clifford Algebra. This is just, well, the name. I mean, you don't really need to know it, but it is good practice to know what algebra this is. Okay, and this, by the way, is something that you have to know. You have to know this. You must know this. Not knowing this, it just won't let you go through. Okay, so this you must learn, understand, memorize. You have to know that an anti-commutator is just like a commutator, but with a minus sign. And also you have to know how to apply it. Now we will do like some minor examples here. Again, we'll have an entire video focused just on properties of the gamma matrices so that you become an expert in them. But yeah, this is the first approach. So now that we found this relation, again, our goal here is to find these gamma matrices. And I told you, right, that this expression here defines the algebra. It tells us everything that there is to know about these matrices. So let's go for it. Okay, so let's write this explicitly. Now, what do I mean? Right, keep in mind this metric tensor here, it has several components and we know what they are, right? We know what the right-hand side is, so that means that we can find out what the left-hand side is, okay? So for example, what is eta mu nu? Let me write it down explicitly, I guess. I was going to just go term by term, but let's be sure. So this is 1, 0, 0, 0, 0. No, that's not 0. 0, 0, 0, minus 1, minus 1, minus 1, and just a bunch of zeros. Okay, so what is eta of 0, 0, for example? So eta 0, 0 is 1, and it is the only element that is 1 in the entirety of the metric. Okay, by the way, if you're using a different metric, what comes next might be slightly different for you, right? If you're using -1 as your 0th element, then this is going to be just slightly different. The same procedure, right? This part is going to be the same, but what comes now is not going to be quite the same, even though the differences will be relatively minor, and in the end, we will get the same result. So, I mean, it doesn't really matter. Just use whatever you like. Okay, so eta of 0, 0 is 1. So let's plug it in, right? So the commutator of gamma 0 with gamma 0, right? Plugging in for eta and mu as 0. This has to be 2 times this value eta mu nu, which is just a number, right? Is 2 times 1 times the unity matrix of n by n, right? We still don't know what the dimensions are. Okay, so this means that gamma 0 times gamma 0 plus gamma 0 times gamma 0 has to be equal to 2 times the unity matrix. Okay, so, but this is simply 2 times gamma 0 squared. So this is 2 times the unity matrix. So for this to be true, we need gamma 0 squared to be the unity matrix. Okay, so this is very important. Now again, if you had used a different convention, then you would have found that this would be minus this, for example, right? If instead of this being 1, it had been -1, right, from there, then you would have found a slightly different result. Okay, so now notice, I mean, we can go for anything else. Let's go for the bunch of -1s, right? We have all these -1s. So if we have eta I I, right, basically eta ij, where I is equal to j, so that's basically what we are doing. And I, again, it is a Latin index, which means that it goes from 1 to 3. It does not start at 0, only Greek letters do that. Okay, so this is minus 1, right? Because eta 1, 1 is minus 1, eta 2, 2 is minus 1, and eta 3, 3 is minus 1, okay? So now let's plug it in again. So we have that the anti-commutator of gamma I has to be equal to, and then we have 2 times, let's see. Yeah, we have 2 times eta mu nu. And eta mu nu is minus 1. So this time we get minus 2 and times the identity matrix. So there. Okay, so now let's multiply through. So we have that gamma I plus gamma I has to be equal to minus 2 times the identity matrix. But these two things are the same. So we get 2 gamma I squared has to be equal to minus 2 times the identity matrix. Again, we can divide by 2. So we end up getting minus 1 is equal to that. So gamma I squared is equal to minus the identity matrix in n by n. Okay, and if you had chosen the other notation for the metric, these two results would have been switched basically, right? So gamma 0 squared would be minus the identity matrix, gamma I squared would be plus, right? But it's the same. It's going to be equivalent. Okay, so now we found the results for these cases. Now let's go for other cases. So we have used these. Now we need to include all of our zeros. Okay, so we have 2 different cases here. So for example, we can go for these ones or these ones. So basically we can go for eta 0 I, right? And of course, this also will encompass eta I 0, right? Which again is this row and this column. Yeah, of course, not including the 1, so only that. Okay, so let's plug it into our formula again. So we have that the anti-commutator of gamma 0, gamma I, this will be 2 times, now eta mu nu. Now, in all of these cases, it's going to be 0. So we get 2 times 0, so this is simply going to be 0. So these will anti-commute. And when we multiply through, we get gamma 0, gamma I, plus gamma 0. This is equal to 0. And of course, if we had used, instead of this, we could have done gamma I, gamma 0, which is kind of for the other case. We would get the exact same thing, except that we would first sum this and then this, right? We would get gamma I, gamma 0 plus gamma 0, gamma I, but it's exactly the same. Now, the fact that these anti-commute mean that if we have at any point a product that is gamma 0, gamma I, or gamma I, gamma 0, you can write it as minus the other one, right? So if you have gamma 0, gamma I, you can write it as minus gamma I, gamma 0, which basically means you can move this one step to the right by adding a minus sign in front. Okay, so that's going to be a very important relation. Okay, so that's this next important result. And now we have one final case, which is the case of these zeros. Right, so let's see which ones would there be, these ones. Okay, so in that case, we now have eta ij, where I is different from j, because when they are the same, we are here. Okay, so in that case, we have the anti-commutator of gamma I, gamma j, which is going to be equal to 2, and then the value of eta mu nu, which is 0. So again, 2 times 0 times the identity matrix, we end up with 0. And again, this is an n by n dimensional 0. I didn't write it down here, but just be very clear, that's an n by n dimensional 0. Okay, and here we write it explicitly, so we get gamma I, gamma j plus gamma j, gamma I, this is equal to 0. And this, just like before, means that if we ever encounter gamma I, gamma j, we can rewrite it as minus gamma j, gamma I. Okay, and of course, the other way around, you can write this as minus and this as plus. It's the same. Okay, so these are 4 extremely important relations that you have to know. It's not optional. You have to know this. Whether you want to learn them by memory, whether you want to rederive them every time from the algebra relation, from the anti-commutative relation, I don't care. Do it however you want. Get a tattoo, put it as the screensaver in your phone or in your computer, or write it in your walls, graffiti it in the streets. I do not care, okay? You have to know this. You have to know this. It's not optional. I cannot stress this enough. You have to know this. Okay, so with this choice, we can, by the way, just quickly show that these matrices indeed would allow us to have what we want. So what we would like to have is that if we apply, right, we have p slash acting on our wave function. This is equal to m acting on our wave function. And if we multiply by p slash, which would give us p slash psi, this is m p slash psi. On the left-hand side, this is by definition p squared psi. And here we have m times p slash psi, which is m psi. So we get m squared psi. So, you know, just quickly corroborating that indeed this gives us the result that we want. So this work was not for nothing. Now let's turn our attention to trying to find the actual matrices. So we can choose any of these matrices to be diagonal, and let's begin taking a look at gamma 0. So gamma 0 squared has to be the identity matrix. So if gamma 0 is comprised of, I don't know, like some coefficient b1, b2, right? It is diagonal, so b3, b4, well, etc. This is also going to be etc. So ... all the way up to bn, since this is an n by n dimensional matrix, and everything else is 0, so big zeros, right? We want this squared to be equal to the identity matrix. So that means that each one of these elements, b1, b2, b3, blah, 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 squared has to be either plus or minus 1, right? Because so that when we square it, we get 1. All right, so we know that all these bi's have to be either plus or minus 1, all right? So that is, and of course here I would go from 1 all the way to n. So that is what we know for now about the gamma 0 matrix. Now we will do a little trick that is going to be used so often, and that is playing around with the traces of combinations of matrices. So right now, let's say that we have any particular I, and we go for gamma I, gamma 0, gamma I. Okay, here I guess I'm kind of abusing notation, so maybe instead of calling this I'm going to call it A or something, just A and A. So this I is of course referencing the I's that we are using right here, right? So these I's. So if we want to find this trace, and this will be done very, very, very frequently, by the way. Now, the first time it may be like, whoa, why are you using the trace? It's such a random thing to do. And yeah, it is kind of random, but it's a hugely strong and important trick. So the trace of the product of these 3 matrices is going to be the trace of, and now let's use some of the properties that we discovered. We know that we can anti-commute gamma I and gamma 0, so we can commute any of them. So let's just put this one there. So we get minus gamma 0, gamma I, gamma I. But what is gamma I squared, right? We already saw that. Gamma I squared is minus the unity matrix. Now, let's omit the unity matrix because we are going to have to write it down in literally every single equation. So from now on, we will not write it, but it will be implicit. Okay, so this is the trace of minus gamma 0 times minus 1, which again, this is because of the unity matrix, which we're not writing down. So minus minus, this is plus, So this is simply the trace of gamma 0. Okay, that's why we chose gamma I, so that we could use the anti-commutator to end up just with the trace of gamma 0 so that we could study gamma 0. Now let's go back to this initial expression and keep in mind that there is a very important trace property. Now you may have seen this in like linear algebra or something. If not, it doesn't matter. I mean, this is simply a property from matrices. You can go ahead and see the proof if you want. It's not terribly complicated or anything. So this is equal to the trace of BCA, right? So it's cyclic, right? We can move these two to the left and this one to the other end, and it is still valid. And we're going to do this with what we have here. So the trace of gamma I, gamma 0, gamma I, this is equal to the trace of, and now we move this one to the right and these two to the left, right? So we end up with gamma 0, gamma I, gamma I. But gamma I squared is minus 1, so we get the trace of minus gamma 0. So what's going on? Using one method, we found that the trace is equal to the trace of gamma 0. But now we found that the trace is equal to minus the trace of gamma 0. So if this trace is equal to this and the same trace is equal to this, it means that the trace of gamma 0 has to be equal to the trace of minus gamma 0. But since the trace is basically just the sum of the elements in the diagonal and gamma 0 is diagonal, we can simply take the minus sign outside. So we get that the trace of gamma 0 has to equal to minus the trace of gamma 0. And there is only one number for which that is true, and that is 0. So that means that the trace of gamma 0 is equal to 0. Okay, so that is very, very, very important, because this means that if all of our elements are either plus or minus 1, then we need there to be the exact same amount of plus and minus 1 elements. Okay, so this means that if we have to have the same amount of plus and minus signs, that means that n needs to be even. So we just found our first piece of information about what these matrices are supposed to look like. So let's write this down, right? So if n has to be even, it means that we can write it as 2 times some other n. And the simplest possible case is where n is equal to 1, which means that we are in 2 dimensions. So we know that in 2 dimensions, we have the Pauli matrices, which there are 3 of. And if we combine them with the unity matrix, we can span the entirety of the 2x2 space. So that means that any other matrix will be a linear combination of them, right? So we can define a 4 vector, sigma mu, which will be our gamma mu in this case, which will be the unity matrix in 2x2, comma, our Pauli matrices. But the problem is, right, what happens if we now go ahead and evaluate the expression that we found previously, right? So I'm going to first write it in generally. So gamma mu, gamma nu, right? The anti-commutator of these has to be 2 times eta mu nu times the identity in 2x2. Okay, so in this case, with the Pauli matrices, we will have that sigma mu, sigma nu anti-commutator has to be equal to this. But we know what the anti-commutator of the Pauli matrices is. It is 2 times delta mu nu times the unity matrix in 2x2. But the delta and the metric are not the same, right? So the metric is 1 minus 1 minus 1 minus 1. Delta is 1 1 1 1 1 0 0. So this is not the same, right? And in fact, this means that in just 2 dimensions, we just cannot find 4 matrices that anti-commute in the way that we need for our physics to work. So unfortunately, this is no bueno. This just does not work, right? If the Pauli matrices together with the identity matrix, which can create any other matrix, right, by linear combination, if no linear combination of them can give us the anti-commutative relation that we need, then yeah, this is just not gonna do it. So we need to go to the next case. So now we go to n equal 2, which will give us small n equal 4, right? So we're gonna be in 4 by 4. Okay, so what now? Now here there are a lot of different possibilities, like a lot. So the one that I will use in this video, even though it does not matter which one you use, right? Physics is independent of the representation. I will be using the Pauli Dirac representation, which is the unity matrix 0, 0 minus the unity matrix. And this is the lazy way of writing 1, 1, 0, 0, right? This is the unity matrix. Then we have a block of 0, 0, 0, right? Each one of these is a 2 by 2 block. That's just the quick way of writing it down, because as you see, matrices are getting really, really big, and it's kind of annoying to write them down all the time. So this is gamma 0, and our gamma i's will be 0, sigma I minus sigma I. Here, sigma i's being the different Pauli matrices, and I, of course, 1, 2, 3. Okay, so this is one possibility, but there are quite a few others, so let me show you another one. There also, so this is the Pauli Dirac representation. It goes all the way down here. And we have another possible representation, which would be that gamma 0 is equal to 0 times the identity, and then identity 0. You can see that this also has a trace 0. Just that it's not a combination of ones and minus ones, but it still has, it satisfies the same property. And we have that the gamma i's are going to be 0, sigma I minus sigma I 0. So that part is the same. So we're basically changing the choice of gamma 0. And this is the Weil representation. So this is another one that is used very often. I think Peskin-Schroeder uses this one, even though I'm not entirely sure. But again, the choice of representation is irrelevant. Any that you use is going to be correct, but different people have different choices, so it doesn't matter. I'm going to use the Pauli Dirac representation for now, but we may use different ones at times just to make sure that we are comfortable with them all. And of course, we can see that this does indeed satisfy the property that gamma I squared is minus 1, by the way, just in case we wanted to check that. Okay, I didn't go through the derivation of this gamma matrix entirely because we're just using these 2 by 2 blocks that can span the entire space. So of course, using the Pauli Dirac matrices just ensures that we can find this. All right, so now we've found our gamma matrices. So let's go ahead and actually begin working on the physics that we want to do. So let's go back to our equation, right? P slash acting on psi has to be equal to m psi. So what is P slash? This is going to be gamma mu P mu psi. And actually, let's put this to the left. So m slash equal to 0. And this will be gamma mu P mu minus m, all of this acting on psi, and that is equal to 0. Let's now continue simplifying this. So let's put in what P mu is, right? It is I h bar times the derivatives. So since h bar is 1, we get gamma mu I d mu. So let's now take the I in front and open this product up, right? Let's go for the 0th element, which will be gamma 0 d0, right? The d0 here, of course, being simply the time derivative. I'm just using a different notation so that we can be comfortable with them all. And then plus I, gamma I, times the I derivatives, which we can, of course, just write as nabla. And then minus m times psi is equal to 0. And now we want to find a way to write this a bit neater, right? A bit more nice. So we multiply from the left. Now it's very important to specify where we are multiplying things from the left or from the right, because not everything commutes. So we have to be careful. So multiplying from the left by gamma 0, we get I gamma 0 squared, right? So gamma 0 squared d0 plus I gamma 0, gamma I, nabla minus gamma 0, m. This is equal to 0. And here we can use a nice little property. We know that gamma 0, this is going to be 1. So no need to worry about it at all. And now let's separate this. So we have all of our gamma things here, and the time derivative doesn't have a gamma. So we have I d psi dt, now writing it explicitly, and this is equal to everything else, which will go to the other side. So this is going to be equal to minus I, gamma 0, gamma I, nabla plus gamma 0, m, acting on psi. And now we will introduce a new notation to make this a bit neater. And we will say, okay, alpha vector, so an alpha vector will be gamma 0 times gamma I, right? So there's 3 of these, one corresponding to each value of I. And we will say beta will be gamma 0. And using this notation, we can rewrite the equation that we have as minus I, and then we have our alpha vector dot nabla plus beta m, all of this multiplying psi. So now let's keep in mind that our momentum vector here is going to be minus I nabla. So what we have here, this is simply going to be this right there. We can take out the minus I nabla so that we end up with a dot the momentum vector. And here we have it. This is the famous Dirac equation for a single particle, and we will be diving into it very, very shortly, but this equation is going to be amazing, right? This equation, you can see, is linear in both time and space. It is first order, it has everything that we would dream of, but of course it's a matrix equation. It's going to have very complex solutions, and I don't mean complex in the way that, you know, they have eyes. Yeah, that's going to be quite tough, but it's going to be very, very interesting, and we will devote the next few lectures in trying to understand it and solve it. Now, just to finish this off, let us find some properties of the alpha and beta matrix, just to make sure that we are very clear on what's going on. So the anti-commutator of B with itself, we already know what it is, because beta, not B, sorry, because beta is simply gamma 0. So this anti-commutator is simply the anti-commutator of gamma 0, which we already know. This is going to be 2 times eta 0, 0 times the unity matrix. So this will simply be 2. So none of that is new. So yeah, no worries there. But what about the other one? So what about the anti-commutator, for example, of alpha I, comma alpha j? So in this case, well, let's multiply through. So this is the same as alpha I, alpha j, plus alpha j, alpha I. But what are the alphas? Where alpha I is simply gamma 0, gamma I, and alpha j is gamma 0, gamma j. And then we have alpha j, which is, well, again, that's gamma 0, gamma j, and alpha I is gamma 0, gamma I. So here what we'll do is just use the anti-commutator of gamma 0 and gamma I a whole bunch of times. And as we saw, they anti-commute. So I can write this as minus gamma 0, as minus gamma I, gamma 0, and then we have gamma 0, gamma j. And then I can also anti-commute these two, so I get minus gamma j, gamma 0, gamma 0, gamma I. But we know that gamma 0 squared is 1, so I end up with minus gamma I, gamma j, minus gamma j, gamma I. So what happens here? Well, what happens if I is equal to j? Well, in that case, I get minus gamma I squared minus gamma I squared. And we know that gamma I squared is minus 1. So I get minus minus 1, which is 1, minus minus 1, which is 1. So I end up with 2. And of course, never forget, this is all multiplied by the 4x4 unitary matrix. Okay, now what happens if I is different from j? Well, in that case, I end up with, this would be minus gamma I, gamma j. I can factor out a minus sign, so I get minus gamma I, gamma j, plus gamma j, gamma I. Okay, and we have seen that in the past. Just let me figure out where. Let's see, where was it? Somewhere here. No, not there. Down here. Gamma I, gamma j plus gamma j, gamma I is equal to 0, right? They anti-commute by definition of these matrices because of the Clifford algebra. So this is simply 0. Okay, so this means that if we put all of this together, right? This means that alpha I, comma alpha j, right? Its anti-commutator is going to be 2 times. Now what happens? If I is equal to j, it is the unitary matrix times 2, and if not, it is 0. So that means that we have to put here delta ij up here, of course, because that's where our other indices are. Delta ij times, well, the unitary matrix, even though it's not really necessary that we write it down. Okay, so here we wrote down both of these results together. Okay, now let's go for the case for the anti-commutator between any alpha and beta. Okay, so here we have gamma 0, gamma I, but actually let me go step by step. So that what I just wrote is alpha I beta plus beta, that is not alpha, alpha I. So alpha I is simply gamma 0, gamma I beta plus beta, gamma 0, gamma I. Okay, but what is beta? Beta is also gamma 0. So we can just write it as gamma 0. And now we can anti-commute these two so that we get minus gamma I, gamma 0. And then we have this gamma 0, which is 1, so we get gamma I. But this gamma 0 squared is also 1, so we end up with 0. So there we go. These are the properties of the alpha and beta matrices that will tell you how they behave. And it's also a little bit of an exercise that we can use to just understand the gamma matrices more. So there we go. That's it for this video. We have derived the Dirac equation, and we also have some notion of what the gamma matrices are, how they behave, and also what these alpha and beta matrices are, which, just come from the gamma matrices. They're just combinations of them, so it's also the same, right? So in the next video, we will begin solving the Dirac equation. And yeah, that's going to be really, really interesting and fun. So I hope I'll see you there as well. So thank you very much for watching. If you enjoyed the content, make sure to leave a like on the video, comment, and subscribe. And maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.